Welcome to 5G Technology World, and today we are speaking with Martin Ridderford of Planet Computers, a company based in London. And Planet Computers has developed a rather unique 5G smartphone. The phone is different in that it uses a mechanical keyboard, something you may have been familiar with in phones from a few years ago. But this one is different in that it's not the traditional simple slide keyboard where the two planes, you might say, the keyboard and the screen are sort of parallel. This one, in this case, the main screen will slide out, revealing the keyboard, and will tilt up. So it's almost like a small laptop, or think of it as perhaps a tablet with a keyboard. It's that kind of orientation. And that seems like a very difficult mechanical design to make it work properly. And Martin is the designer of that. And Martin, by the way, also designed many products for Psion back probably about in the early 90s or so. Yep. And I had the pleasure of being able to work with Psion, actually developing peripherals for some of their early products. And if you've ever seen a Psion product, you'll know that the mechanical designs are works of art. They're just beautifully done, and I've always been impressed by them. Martin, why don't you tell us about this slide up and then tilt mechanical design?
Okay, the rationale behind what we're trying to do here is that this is the third generation of product we've developed, and the first two were based on trying to bring the Psion type of product back 20 years later to smartphone users. So the notion is that you have in the Psion Series 5 that we developed, the keyboard was always deemed to be very usable, even though it's small and diminutive, but it's just about able to be touch typable. And we wanted to take that keyboard and merge that with smartphone technology. And interestingly, over the years, when we started doing the Psion kind of products, as you know, a keyboard is kind of twice as wide as it is tall, but screens in those days weren't. So if you tried to marry a screen with a keyboard, a typical screen with a keyboard, they're not the same shape. You know, the screens used to be much taller, almost square. The keyboard's quite long and narrow. So we developed on the Series 5 what we called a letterbox screen, and we married the two together. So basically the screen and the keyboard are the same shape, made a neat package. When we were doing the Planet products, interestingly, smartphones have now moved to this letterbox kind of shape, 2:1 kind of aspect ratio. And so suddenly we've got screens, the world's best touch screens, the same shape as a keyboard. So it seemed natural to marry a keyboard with these new screens. So we started off with the first two Planet products were exactly that. And they were a clamshell format, so opening like a book or like a laptop. We got a lot of publicity for what we were trying to do. It's sort of seen as retro, but actually it's a very usable format to have a small handheld device with a keyboard in it for, select people. Having developed the previous one a couple of years ago, we wanted to come out with a new improved version because we want to have a 5G version of it. And we set ourselves a challenge of actually doing the ultimate product, which is to have the screen, as Martin said, we basically have the screen and the keyboard directly underneath the screen. So both of them facing up. So when you've got a smartphone, and you're handling it just like a smartphone, it behaves just like a smartphone, and you can do everything you can and want to do with smartphone. But hidden underneath, when you slide the two pieces apart, is a Scion style keyboard with proper tactile keys, correctly spaced so that you can touch type on it with not much difficulty. But you can also use it in the air if you like. You don't have to put it on a surface. We established what we wanted to do, which was to move the screen and reveal the keyboard. Traditional mechanisms, which people, there have been quite a lot of slide phones in the past, tend to fall short of what we want to achieve when the device is open. So when the device is open, we want it to be a laptop-like thing. And as Martin says, a laptop is more or less all the same plane. And basically, so the edges, the back edge of the keyboard and the front edge of the display are kind of joined together, if you like. Traditional slide mechanisms tend to leave the display on top of the keyboard element, which basically does two things. One is it restricts the space for the keyboard. And secondly, almost more important, is that the top row of keys is compromised by the step up to the display. So if you've got nails or something like that, it's a bit awkward to get to that top row of keys. So you end up with an interesting product and form factor, but not something which is very good for typing on, because it's got a restricted keyboard and it's got this restricted top row. So our ambition was to open it up, have it slide open, but end up in the same format as our previous products, where because they hinged open, everything was at the same plane, and it acts like a sort of slightly angled tablet. It feels very solid in your hands and is easy to use for typing and things. Okay, so that sort of sets what we were trying to do. Just go back to the previous products. The other thing that we found was that because the previous products were open like a book, the outside display, because it's a phone as well, was compromised. So we had this small little display on the outside, and it's much better, obviously, to have it that you see the whole screen on the outside. So this is where we're aiming. So we had this ambition to slide the whole thing apart, and I like challenging myself. So over Christmas, I worked out a way of doing it. And the difficulty is, obviously, we've got a full keyboard, and you don't want to break into that surface at all. And you've got a full display, and you can't obviously break into that surface. So you've got two surfaces, and you're trying to join the two together in a strong and robust way. And how do you do that? So basically, the mechanism exists. It's kind of like a drawer mechanism, whereby you have these rails down the sides holding the drawer to the carcass of the drawer unit, and you have an intermediary sliding bit. So basically, when you pull the drawer out, there's often an intermediary bit, and then there's the slider. So we're using the same technique. We have this intermediary bit, which we call a carriage, and when you slide the two bits apart, that intermediary bit bridges between the two in a sort of slightly unusual way. But because you've got that intermediary bit, we can then pivot the display off it and tilt it forwards and bring it back into plane. So that sums up the sort of the technical, main mechanical element, but actually making it work and making it robust is quite an exercise. So although the principle's reasonably straightforward, it hasn't been used before, as far as I know, and it's fraught with mechanical problems because it's small and has to be strong.
Did you have to go through a few iterations to get it right?
Yeah, we do. Yeah, we did. So I tend to, because I am working in mechanical mechanical things, I tend to make models in order to explore how things work. So what I might do is just quickly nip behind me and just pick out a couple of these models and show them in front, because it actually shows the design process in quite a sort of interesting way. This is the first model. Can you see that okay?
Yes.
It's made out of black plastic and some brass elements. So this basically has that mechanical mechanism in it, and it has some other sort of features, because once you build something, you realize it's got to do other things, or it gets more complicated. But this has that slide action. You can see that slide action there. And then it has the tilt action at the end, and you can see the piece that I was talking about, this intermediary piece here, sticking out the back, and this pivoting relative to it. So that's the basic principle, that this is telescoping inside the base, and this is, this top bit is sliding in here, and there's a spring between them. That spring basically makes this click into its open position, and then it's able to slide here. So there's some magnets at the front, and that goes click. So that holds it in position, in the front position, and then it slides, and then it flips up. So this sort of showed me that, you know, that's a possible way of doing it. I then went to another model, which is exploring the biggest problem, which is how do you connect the two halves together? So electrically, they have to be connected together. We did think about using Bluetooth between the two halves, but that means having batteries in both halves, and it adds another level of complexity. So I preferred to have the two directly connected. So this is what we call a 2 times full size model. Again, it's just a slice, but it's just showing you, again, the thought process. And this is, again, another hand-built model to explore various aspects of the mechanism. So if you can see here, rather than a sort of telescoping element that I had before, I've got these 2 rails, which are round steel elements, and the carriage slides along those rails. It obviously does the same here, and you can see in here there's a piece of material which is acting like the flexible PCB that goes between the two. So I can, through this kind of mechanism, through this kind of model, I can explore what's going on with the cables and various other aspects of the mechanism, and this is typically how I tend to work. And then once I've done this exploration, we can go into the CAD and build the model, knowing that we've got some principles that work. So as I say, that's the sort of second stage. The first stage was proving that the principle works, and then this is working out in more detail some of the more subtle elements.
How did you build some of the pieces there? Were they 3D printed, or were they injection molded?
No, these are just hand fabricated by me in the workshop with a bandsaw and a circular saw and a sander and a drill, you know, and a milling machine. It's kind of, you know, an old school way of doing it, but it's very immediate. You get your hands on something, and you get a feel for what works and what doesn't quite quickly. Whereas if you're developing something in the CAD, computer-aided design, in the computer, you find that, you know, you're zooming in all the time, and everything looks so big, but when you actually see it in reality, it's tiny. So, you know, and almost unhandleable or unmakeable, you know, some of these bits. Whereas, you know, especially if you're working 2 times full size, you can work on them, but you realize that, you know, it's viable kind of thing.
Did you work on any other aspects of the design other than the rails?
In terms of different ways of doing it, is that what you mean?
Well, in terms of the overall layout of the phone.
Yes, yeah, I tend to do that in parallel. That I tend to concentrate on the things which are the most difficult first, just to make sure that I'm happy about the direction it's going. I've set myself a challenge in terms of getting these bits to slide and move, you know, relative to each other and do what I want them to do. So I've got to make sure that I can achieve that in reality. And then it's all about how you fit that into a small handheld device. And so you're looking at all the implications, the 3D implications, what has to go where in order to get it to work properly. And then you start looking at what the ID looks like. In some ways, the ID is quite simple because we want it to look like a smartphone when it's shut, and we want it to look like a laptop, mini laptop when it's open. So you could argue that the ID is quite straightforward. There's a lot of subtle detailing around the edges because we've got a keyboard. We want the gap between the keyboard half and the display half to be as neat as possible, but we also want the keys to be accessible. Because you've got one bit sliding against the other, we have to recess the keyboard, as it were, in the way that laptops do it. We have a border which recesses the keyboard slightly, but also at the sides we expose the keyboard to make it feel like it's up, if you like. So there's a lot of subtle kind of thinking required in order to get that movement to work and get it to look and feel really good when it's open.
Well, based on what I've seen from the Scion products, I'm sure it's quite impressive. Did this mechanical design put any strains or limitations on the electrical design that the electrical designers might have come to you because maybe, for example, where you place the battery and where, heat dissipation and things like that? Did it affect the electrical design, and how did they get around some of that?
Yeah, so because this is the third generation that we've worked with our Chinese manufacturers, the first generation we changed the way we basically, because we've got a screen element, just like a laptop, a screen element and a keyboard element, we have to decide where each of the main components goes. So it's possible to construct it like a laptop where you just got the screen in the lid and everything else is in the base, but that's not the way that phones are made. So phones, obviously, everything is in one package. So what we're doing here is stripping out some of those elements, and we went down the route that we wanted the PCB, the main PCB, and the display to be in the lid with all the antennas and everything, and the speakers and the earpieces and things all in the lid, and then the base contains the keyboard, connectors and battery. So that's the split that we've worked with on the previous two products, and we're assuming the same split at the moment for this, but actually it's more possible to swap things around if we chose to, but we're assuming the same split. So it's like a smartphone, the top element, in as much as you've got a display and then the PCB directly underneath it. And the way that smartphones are constructed, they put a heat sink element between the display and the PCB in order to spread the heat out from the chips. So we go the same route. So there should be no unknowns for a manufacturer who's used to making smartphones in making this device, because, as I say, the elements are the same.
Well, I see the advantage of having the battery in the keyboard section because that gives you some mechanical stability. I was wondering about that in terms of if the battery was in the smartphone section, it seems to me it would tip over, and it would be too heavy, too top heavy.
Yeah. So the advantage there is that actually a bit of, as you say, a bit of weight and a bit of bulk in the base is good. And also, we're not so concerned with a smartphone. You're marrying the thickness of the battery and the thickness of the electronics, and you're cutting. They're both on the same plane, if you like. So they're both cut back in order to fit in. We have the advantage in putting it in the base of having a big plan area for the battery, much bigger than you would normally have. And also with this design, because we have a mechanism down each side, there is a requirement for thickness for that mechanism. So the space for the battery is quite generous. Interestingly, because this is on Indiegogo, we get feedback from early backers. Most of them want no compromise on the battery. They want 5,000 milliamp hours on the battery. We managed 4,000 on the previous devices. There's no reason why we can't have 5,000 on this. So I think that's the way this is going to go, is that the base has to be whatever thickness it needs to be to have a 5,000 milliamp hour battery. That's the target anyway.
Well, it seems that without having the battery in the phone section, that opens up a tremendous amount of space to work with.
Yeah, well, in fact, sorry, carry on.
And for example, I believe the phone has at least one, maybe it was a two USB Type-C connectors and things like that. Where did you put them? Are those on the phone side or on the keyboard side?
They're on the keyboard side. So all of the connectors come down just like a laptop, so that the connectors and things are where you expect them on the sides. So that works out very nicely. Obviously, each one of those connections has to go through the hinge, but you know, the number of ways to those connections is not that great. So as I say, that arrangement works pretty well. The other thing we did on the first two devices was actually, normally on a phone, they have a very small amount of real estate for components on the PCB, and they tend to populate it on both sides. And they're happy to do that because they don't mind it getting thicker because the battery's thick. With our device, we want that to be as thin as possible. So actually we did something pretty unique, which was to make a single-sided board, much bigger area, but it was single-sided in the lid of our previous devices. And again, I'm assuming we'll probably go the same way because that gets the thinnest possible lid. So we're looking at sort of clever ways of minimizing thicknesses, and to minimize the thickness of the lid is a really good thing to do. We're not so concerned about the base because of the, as you say, the stability and things like that. We want to give it a good battery as well.
Okay, well, Martin, thank you very much for your time. That was a fascinating description of how to do a rather unique mechanical design. And I wish you great success with this phone. I would love to have my hands on one. I'd love to see how it works. Maybe.
Well, hopefully in about a year's time, we'll all have our hands on one.
Okay, well, thank you very much.
Thank you.